124 light-years from Earth in the constellation, Leo, a small reddish star, is being watched more carefully than almost any other star in the sky. The reason is the planet that orbits it. Its name is K2-18b. It is roughly 2.5 times the size of Earth. It sits in the part of its star's habitable zone where liquid water could exist, and it is one of the very few worlds in the galaxy where the James Webb Space Telescope has been able to look directly at the atmosphere and find something. What it has found is not aliens. Not exactly. What it has found is a set of chemical signals that some scientists believe are the first hint of life beyond Earth, and that other equally serious scientists believe are statistical artifacts in the data. The argument is real. The signal is real. What it means is the open question. Methane is in that atmosphere. Carbon dioxide is in that atmosphere. And there may or may not be a molecule that on Earth is produced almost entirely by marine plankton. If you find yourself drifting off to these long, careful cosmic mysteries, hit like and subscribe to Cosmic Drift. Now let us drift outward across 124 light-years to the planet that won't stop sending signals nobody can quite agree on. The journey begins in a way with a single press conference held in Cambridge, England in April of 2025. A team of astronomers led by a man named Nikku Madhusudhan stood in front of a microphone and announced that they had found the strongest hints yet of biological activity outside our solar system. The data came from the James Webb Space Telescope. The molecule was a sulfur-bearing compound called dimethyl sulfide. The confidence level was 3 sigma, which in physics means the result has roughly a 0.3% probability of being a chance fluctuation. Madhusudhan's team had checked their work carefully. The signal was consistent across multiple independent reductions of the data. It survived the various robustness tests they applied. From their point of view, the case for something interesting was strong, and the most natural interpretation was that K2-18b might host life. That was the morning of April 17th, 2025. The paper appeared in the Astrophysical Journal Letters that same day. The headlines went around the world within hours. The Cambridge press release used the phrase "a Hycean world," with an ocean that is teeming with life as the scenario that, in the team's view, best fit the data. And then beginning within days of publication, the response from the broader scientific community arrived. It was not a celebration. It was a careful, sustained multi-author challenge to the statistical foundations of the claim. Within 4 months, 3 separate reanalysis papers had appeared using the same JWST data, reaching different conclusions. The certainty of that morning in Cambridge began slowly to come apart. This story is about that argument, about a real planet, a real telescope, a real signal in real data, and a real disagreement among working scientists about what the signal actually means. It is one of the more honest and unresolved chapters in modern astronomy, and tonight we are going to walk through it carefully and slowly with all the time you need. I want to acknowledge something at the start because it sets the tone for everything that follows. The question of whether other worlds harbor life is one of the oldest questions human beings have asked. People have wondered about it for as long as we have records of people wondering about anything. Most of those people had no chance of getting an answer because they did not have the tools or the data to even meaningfully approach the question. The wondering was abstract. It happened in poetry, in philosophy, in religion, in early science fiction. The actual evidence to settle the question was always, for most of history, completely out of reach. What is happening with K2-18b is one of the very first concrete data-driven attempts in the history of our species to actually examine a specific candidate world and ask with real instruments and real measurements whether it is inhabited. The argument that has unfolded around the planet is not a sign that the question is unanswerable. It is a sign that the question is finally being asked in a way that admits of answers, and that the answering process is hard and slow and does not produce instant results. We are alive at the moment when the question began transitioning from abstract to concrete. That is in itself worth a moment of attention. Before we get to the planet itself, before we walk through the chemistry and the controversy, I want to set the larger frame. Because what is happening with K2-18b is only possible because of two enormous changes in astronomy that have unfolded over the last 30 years. The first is the discovery for the first time in human history that planets orbiting other stars exist in measurable numbers. The second is the construction of a telescope capable of analyzing the atmospheres of those planets directly. Without either of those changes, K2-18b would still be there doing whatever it does, and we would not even know it was there. Both changes are recent. Both happened within the lifetimes of most people listening to this script. Until 1995, humanity had never confirmed a single planet orbiting another sun-like star. The question of whether such planets even existed was a serious, open scientific question for most of the 20th century. Astronomers assumed they probably did based on theoretical arguments about how stars form and the residual material left over from that process. But assumption is not detection. The technology to actually find such a planet, given how dim it would be, next to the glare of its star and how subtle its gravitational effects would be on the stars, motion simply did not exist for most of the century. People tried. There were claims, all of them eventually retracted or revised. Until 1995, the count of confirmed exoplanets around sun-like stars stood at 0. That changed in October of that year when two Swiss astronomers, Michel Mayer and Didier Queloz, working at the Geneva Observatory and observing from the Haute-Provence Observatory in southern France, announced the detection of a planet orbiting the star 51 Pegasi. The star itself is a quietly ordinary sun-like star about 50 light-years from Earth, visible to the naked eye on a clear night in the constellation Pegasus. The planet, which got the catalogue designation 51 Pegasi b, was a gas giant, roughly the mass of Jupiter, but orbiting its star at less than 1/20th of the distance between the Earth and the Sun. The orbital period was 4 days. Nobody had expected to find a Jupiter-mass planet that close to its star, because nothing in the solar system looked like that. And for decades the assumption had been that other systems would broadly resemble ours. The 51 Pegasi b discovery shattered that assumption in a single observation. Planets, it turned out, came in arrangements that nobody had predicted. Mayer and Queloz received the Nobel Prize in Physics in 2019 for the discovery, sharing the prize with the Canadian-American cosmologist James Peebles. By the time the prize was awarded, more than 4,000 additional exoplanets had been confirmed using the same general approach Mayer and Queloz had pioneered, plus several others. The 51 Pegasi b detection had not just opened a new field, it had launched one of the most productive scientific accelerations of the early 21st century. By the early 2010s, exoplanets were being detected by the hundreds, and then by the thousands. By the mid-2020s, the running total had passed 5,000 and was approaching 6,000. Most of those discoveries came from a single space telescope. The Kepler Space Telescope, launched by NASA in 2009, was designed to do one specific thing, which was to stare at a single patch of sky in the constellation Cygnus for years on end and watch for the tiny dips in starlight that occur when a planet passes in front of its star from our line of sight. Kepler found thousands of planets this way. It transformed exoplanet science from an exercise in finding rare individual examples into an exercise in statistical population studies. It became possible for the first time to ask what the average planet around the average star looks like, because we had enough planets to compute averages. The answer turned out to be that most stars have planets, that small rocky planets are extremely common, and that planets in the so-called habitable zone, where liquid water could potentially exist on the surface, are present around a substantial fraction of the stars in the galaxy. Kepler's mission was extended in 2014 after a malfunction left it unable to point with the precision required for its original survey into a different observing program called K2. The K2 mission used the sun's radiation pressure on the spacecraft itself to keep it stable, allowing it to observe different patches of sky for shorter campaigns. In 2015, during one of those K2 campaigns, the telescope detected the periodic dimming of a small reddish star in the constellation Leo. The dimming repeated every 33 days. The pattern indicated a planet roughly 2.5 times the size of Earth, in an orbit close enough to the star to be in its habitable zone. The planet was given the catalogue name K2-18b, the host star K2-18. That was 2015. The detection was announced and catalogued, but not immediately treated as exceptional. There were many such candidates from K2. K2-18b sat in the queue of interesting potentially habitable planets awaiting follow-up. In 2017, the planet was independently confirmed using ground-based radial velocity measurements, which detect the gravitational tug of a planet on its star by looking for the small Doppler shifts the tug produces in the star's spectrum. With confirmation, K2-18b joined the growing catalogue of small rocky or icy worlds in the habitable zones of nearby red dwarf stars. It was an interesting target, but not yet a famous one. What made it famous was a second technological transformation, which arrived several years later, to go beyond simply confirming that a planet exists, and beyond knowing its rough size and orbit, to actually study its atmosphere and ask what gases are present in the air. You need a telescope capable of doing transit-transmission spectroscopy. That is the technique we are going to walk through carefully, because it is the foundation of everything that follows in this story. Here is how transit-transmission spectroscopy works in plain terms. When a planet crosses in front of its star, as seen from our line of sight, a small fraction of the starlight passes through the upper atmosphere of the planet on its way to us. The fraction is tiny. For a planet like K2-18b, perhaps 1 part in 10,000 of the total starlight is filtered through the planet's atmosphere during a transit. But that filtered light carries information. Different gases absorb light at different specific wavelengths. Water vapor absorbs at certain infrared wavelengths. Methane absorbs at others. Carbon dioxide has its own characteristic absorption features. So does dimethyl sulfide. So does ammonia. If you can take a spectrum of the star during a transit and compare it to a spectrum of the same star outside the transit, the difference tells you which gases are present in the planet's atmosphere by their absorption signatures in the small fraction of starlight that pass through the planet's air. The technique is conceptually simple and operationally extremely difficult. You are looking for changes in stellar brightness at specific wavelengths of perhaps a few parts per million against a background of a star that itself has spectral features that change with stellar activity, with rotation, with star spots, with all the other complications of a real astronomical source. Any small instrumental drift, any imperfectly subtracted systematic, any unmodeled effect in the data reduction pipeline can produce a feature in the resulting spectrum that looks like a molecular detection, but is actually noise. For ground-based telescopes, the Earth's atmosphere itself adds enormous additional complications, because Earth's air is full of the same molecules you might be trying to detect on the planet, and disentangling the two contributions requires careful corrections. For space-based telescopes, the corrections are simpler in some ways and more complicated in others, but the basic precision required is at the very edge of what is currently achievable. The James Webb Space Telescope, which launched on Christmas Day of 2021 and began science operations in mid-2022, is the first instrument ever built that can do transit transmission spectroscopy on small habitable zone planets around red dwarf stars at the precision required to detect specific molecules in the atmosphere. The Hubble Space Telescope before it had done some atmospheric work on hot Jupiter planets, large gas giants in close orbits, where the signals are relatively easier. But for small planets in habitable zones with relatively cool atmospheres and relatively shallow transit signals, JWST is essentially the first capable instrument. It is also currently the only one. The next generation of telescopes that might be able to perform similar work, including the proposed Habitable Worlds Observatory, are still many years from launch. JWST carries several instruments relevant to exoplanet atmospheric work. 3 of them figure into the K2-18b story specifically. There is NIRSPEC, the near-infrared spectrograph, which observes from roughly 0.6 of a micron out to about 5 microns. There is NIRIS, the near-infrared imager, and slitless spectrograph, which covers a similar wavelength range with a different optical configuration. And there is MIRI, the mid-infrared instrument, which observes longer wavelengths from about 5 to 28 microns. Each instrument has different sensitivities, different wavelength coverage, and different systematic effects. The full picture of an exoplanet's atmosphere, when JWST observes it, comes from combining results across these different instruments. Methane shows up most strongly in certain near-infrared bands. Dimethyl sulfide has features in both near-infrared and mid-infrared. Carbon dioxide has its strongest features in the 4-micron region accessible to NIRSPEC. Building a complete model of what is in the atmosphere requires data from across the instruments, plus careful attention to where each instrument's strengths and weaknesses are. I want to pause for a moment on what it means as a piece of engineering that we can do this kind of measurement at all. JWST sits about 1 million miles from Earth at a gravitationally stable point called the second Lagrange point, where the combined gravitational pull of the Earth and the Sun keeps a small object in a stable orbit. The telescope's primary mirror is 6.5 meters across, made of 18 hexagonal segments coated in a thin layer of gold to reflect infrared light efficiently. The mirror has to be kept cooler than about 50 Kelvin, which is roughly minus 400 degrees Fahrenheit, in order to detect the faint infrared signals from distant astronomical objects without being overwhelmed by the telescope's own thermal radiation. A 5-layer sun shield, each layer about as thin as a human hair, blocks the heat from the Sun, the Earth, and the Moon. The instruments at the focal plane are kept at temperatures even colder than the mirror, in some cases below 10 Kelvin. All of this engineering is in service of being able to detect changes in the brightness of distant stars at the level of a few parts per million in specific wavelength bands as planets pass in front of those stars. The fact that the engineering works at the precision is achievable, that we can take spectra of planets 124 light-years away and ask what gases are in their atmospheres, is itself a small miracle of recent technical history, until JWST became operational in mid-2022 No instrument in human history could do this kind of work. Now we have one, and we are using it, among other things, on K2-18b. That is the toolkit, a telescope launched in 2021. 3 instruments capable of resolving molecular absorption features in the upper atmospheres of small planets 100 light-years away. A technique transit transmission spectroscopy, which is sensitive enough to detect parts per million level signals in the right conditions, but vulnerable to systematic errors that can mimic real molecular detections. And that is the toolkit Madhusudhan's team turned in 2023, and again in 2025, on the planet K2-18b. Let us spend some time with the planet itself. Not the controversy, not the headlines. The planet as a physical object sitting in space 124 light-years from Earth, doing whatever it does. K2-18b orbits a star called K2-18. The star itself is a red dwarf classified by astronomers as an M2.55V dwarf, which is shorthand for a small main sequence star with a surface temperature of about 3500 degrees Kelvin and a mass roughly half that of our Sun. Red dwarfs are the most common type of star in our galaxy. Roughly 7 out of every 10 stars in the Milky Way fit this category, which means that the typical star, statistically speaking, is much smaller and cooler and dimmer and longer lived than our Sun. Our Sun is in galactic terms somewhat oversized and somewhat overpowered. The average star is more like K2-18 than like our own. What does it mean to live near a red dwarf? Several things matter. The first is that the star itself is dim. K2-18 emits perhaps 2.5% of the total light that our Sun does, mostly in the redder and infrared parts of the spectrum. To stand on a planet orbiting K2-18 and see the star as bright as the Sun appears from Earth, you would need to be very close to it. The habitable zone, the range of distances where liquid water could exist on a planet's surface, sits much closer to a red dwarf than it does to a Sun-like star. For K2-18, the habitable zone is at roughly 15% of the Earth-Sun distance. Anything farther out is too cold. Anything closer in is too hot. Planets in the right zone are squeezed into a narrow band that by Earth standards would be considered extremely close to the host star. That closeness has consequences. A planet orbiting in the habitable zone of a red dwarf is exposed to much more concentrated radiation in absolute terms in those longer wavelength bands than Earth is from the Sun. The star's light is redder and lower in energy, but the planet is much closer, so the total energy received is comparable. The closeness also tends to drive the planet into tidal lock, where the same face of the planet always points toward the star, similar to how the Moon always shows the same face to Earth. Tidal locking matters for habitability calculations because it produces a permanent day side and a permanent night side, which can disrupt atmospheric circulation in ways that depend on the specific planet's properties. K2-18b is not necessarily tidally locked, but it is close enough to its star that some atmospheric coupling effects from the proximity are likely to be in play. A second consequence of red dwarfs as host stars is that they are typically more magnetically active than Sun-like stars, especially when they are young. Stellar flares from red dwarfs can be much larger relative to the star's quiescent output than the flares our Sun produces. A young red dwarf can subject its planets to bursts of high-energy radiation that over geological timescales can strip away atmospheres entirely. K2-18 itself is thought to be relatively old and relatively calm by red dwarf standards, but the long history of any planet around such a star will have included exposure to significant levels of stellar activity. Whether K2-18b has retained an atmosphere through that history And what that atmosphere is composed of is exactly the question JWST is now being used to answer. A third consequence of red dwarfs as host stars is also a practical advantage for the astronomers studying them. The smaller a star is, the larger the relative effect of any orbiting planet in both the radial velocity wobble it produces and in the transit depth it creates as it passes in front of the star. A planet of given size produces a deeper transit signal in front of a small star than in front of a larger one. The signal-to-noise advantage of observing planets around red dwarfs compared to planets around Sun-like stars is substantial. This is part of why the small handful of planets where atmospheric studies have been pushed furthest are almost all around red dwarfs. The technical access is just easier. K2-18b itself is a sub-Neptune, which is a useful but somewhat awkward category in modern exoplanet science. The term refers to planets that are larger than Earth but smaller than Neptune, sitting in a size range that has no analogue in our own solar system. Our solar system has rocky terrestrial planets like Earth and Venus and Mars, and it has gas giants like Jupiter and Saturn, and it has ice giants like Uranus and Neptune. Between Earth-sized and Neptune-sized, our solar system simply has nothing. Once exoplanet surveys started returning statistics on planet size distributions, however, it turned out that the sub-Neptune category is one of the most common kinds of planet in the galaxy. Roughly half of all stars surveyed by Kepler have at least one sub-Neptune in close orbit. They are everywhere. What sub-Neptunes actually are internally is a more complex question. The size range covers a lot of physical possibilities. A sub-Neptune could be a rocky world with a thick, gaseous envelope of hydrogen and helium, which would make it more like a small gas dwarf than like Earth. It could be a planet with a deep ocean of supercritical water surrounding a rocky core, which would be a kind of water world with no clear surface. It could be, on a few specific theoretical proposals, a planet with a global liquid water ocean beneath a hydrogen-rich atmosphere, which is the configuration called a Hycean world that we will spend time with shortly. The same observed size and mass can be produced by quite different internal structures, and distinguishing among the possibilities requires careful atmospheric measurements, exactly the kind of measurements that JWST is now beginning to make. K2-18b's specific measurements are these. Its radius is 2.61 times Earth's radius, with an uncertainty of plus or minus 0.09. Its mass is 8.63 Earth masses, with an uncertainty of plus or minus 1.35. From these, you can compute its mean density, which works out to roughly 2.6 grams per cubic centimeter lower than Earth's density of about 5.5. The lower density implies that the planet is not a pure rocky body. There has to be a significant volatile component, water and hydrogen and helium and other lighter materials contributing to the bulk. The exact distribution of those volatiles is, of course, the open question. Are they distributed in a deep atmosphere with a small rocky core, in a thick water ocean with a thin atmosphere on top, in a hydrogen envelope around a substantial rock-water mixture? The bulk density alone cannot distinguish among these scenarios. You have to look at the atmosphere directly to break the degeneracy. The orbital configuration is also worth a moment of attention. K2-18b orbits its star once every 33 days. That orbital period puts it in the habitable zone of the cooler red dwarf, where the equilibrium temperature calculated from the star's output and the planet's distance, and assuming a typical reflectivity, comes out to roughly 270 Kelvin. That is around -3 degrees Celsius, or in the mid-20s Fahrenheit. Cold by human standards, but in the range where liquid water can exist on a planetary surface, given the right atmospheric pressure and greenhouse effects. The actual surface temperature, if K2-18b has anything that could be called a surface, would depend strongly on the atmosphere's composition, on the cloud cover, on the planet's albedo, and on whatever heat the planet itself is generating internally. The equilibrium temperature is the starting point for the calculation, not the answer. The orbit, as far as can be determined from the data, is roughly circular with a small eccentricity that does not produce extreme seasonal variations of the kind you would see on a strongly elliptical orbit. The orbital plane is well aligned with our line of sight, which is fortunate because that alignment is what makes transit observations possible in the first place. If the planet's orbit had been a few degrees out of our line of sight, the transits would not occur. The transit transmission spectroscopy technique would not be available, and we would have no way to study the atmosphere at all. K2-18b happens to have a transit-friendly orbital geometry from our vantage point, and that single piece of geometric luck is part of why this specific planet has become one of the most studied targets in modern exoplanet astronomy. Add up these properties and the picture is this: a planet in the habitable zone of a calm, mature red dwarf, about 124 light-years away. 2.5 times the size of Earth, 8.5 times the mass, with a density implying significant volatile content in a 33-day orbit transiting its star regularly enough to be observed by space telescopes. A planet that, given its size and orbit and likely composition, could plausibly host a deep liquid water ocean, a thick gaseous envelope, or some combination of both beneath whatever atmosphere it has retained. A planet that has been a high priority target for atmospheric study since the moment its parameters were nailed down. In 2019, before JWST had launched an early Hubble Space Telescope study of K2-18b, suggested it might have water vapor in its atmosphere. The result generated some excitement at the time, but it was based on Hubble data with limited wavelength coverage, and the water signal was disputed almost immediately by Reanalysis teams, who pointed out that the same Hubble spectrum could be explained by methane, rather than water, given how the two molecules' absorption features overlap in the wavelengths Hubble could access. The Hubble episode is worth remembering because it is in a small way a preview of the larger argument that would unfold around K2-18b a few years later when JWST got involved. The same data analyzed differently can produce different answers. That is just a feature of how atmospheric retrievals work for planets at the edge of detectability. The 2019 Hubble result had been led by Bjorn Benneke at the University of Montreal, with a separate analysis by Angelos Thieras at University College London, also reporting evidence of water vapor. Both teams used the same publicly available Hubble data, and both reached broadly similar conclusions about the presence of some kind of water-related signature in the spectrum. Within months, however, other groups had reanalyzed the same data and pointed out that the spectral feature being interpreted as water could equally well be interpreted as methane, because the two molecules have overlapping absorption features in the relevant wavelength range. The Hubble data alone simply did not have the spectral resolution to distinguish between water and methane in the right wavelength window. The 2019 result in retrospect was not so much a confirmed water detection as it was a confirmation that K2-18b had some kind of identifiable atmospheric absorption that needed better data to fully characterize. That episode set up two patterns that would recur in the JWST era. First, the pattern of ambiguity. Spectral features at the edge of detectability can be interpreted in multiple ways, and the choice between interpretations depends on assumptions that themselves can be questioned. Second, the pattern of public communication outpacing scientific consensus. The 2019 Hubble water claim was treated in many media outlets as a confirmed detection of water vapor on a habitable zone exoplanet, even though the careful papers themselves had presented the result with appropriate caveats. The same dynamic on a larger scale would replay around the JWST observations a few years later. But the Hubble study, whatever its eventual fate, established K2-18b as a particularly interesting target. Whatever was E in that atmosphere, the planet had enough atmosphere to register on Hubble's relatively coarse instruments. That meant JWST, when it became available, would be able to probe much deeper. It was just a matter of waiting for time on the new telescope, getting the observations approved and running them. The waiting ended in early 2023, when JWST observed K2-18b for the first time, using the NIR spec and NIRIS instruments. The proposal had been led by Nikku Madhusudhan and his team at Cambridge. The team had spent years preparing theoretical predictions for what a Hycean world's atmosphere should look like based on careful chemical modeling. They knew before the data arrived what they were hoping to find. They knew what would be consistent with a Hycean interpretation and what would rule it out. When the JWST data came back, the team applied their atmospheric retrieval pipeline to the spectrum, and the answer that came out was in some respects exactly what they had hoped for. The data showed methane. The data showed carbon dioxide. The data more faintly showed something else, a hint of a feature consistent with dimethyl sulfide, the molecule that on Earth is produced almost entirely by marine plankton. The Hycean hypothesis in 2021 had predicted exactly this combination of gases as a possible signature of a habitable Hycean world with biological activity. The 2023 JWST data on the team's reading was consistent with that prediction. That reading, however, was the team's reading. Whether the data actually supported that reading was a question that would dominate the next several years of debate. To understand why we need to understand what the Hycean hypothesis is, where it came from, and why both its supporters and its critics take it seriously enough to argue about it carefully. That is the next step in the descent. The planet itself, as we have just walked through, is a real and well-characterized object. The interpretation of its atmosphere, however, is something else entirely. The Hycean hypothesis was published in the Astrophysical Journal in August of 2021 by Nikku Madhusudhan and two colleagues, Anjali Piet and Savas Konstantinou, all at the Institute of Astronomy at the University of Cambridge. The paper proposed a new category of potentially habitable planet, distinct from the Earth-like rocky worlds that had dominated habitability discussions for decades. The new category combined two simple ingredients: a deep liquid water ocean covering the entire surface of the planet, a thick atmosphere dominated by hydrogen rather than the nitrogen, oxygen, carbon dioxide mix that characterizes Earth's atmosphere. The combination of those two features, hydrogen and ocean, gave the category its name, Hycean, as a portmanteau of the two ingredients. The case for taking Hycean worlds seriously rests on a set of physical and observational arguments that the Cambridge team had been developing over several years. Let me walk through them because they matter for understanding why K2-18b became such a high priority target. The first argument is about how planets form and what they tend to look like. When a planet forms in a protoplanetary disk around a young star, it accumulates not just rocky material, but also volatile substances, water, and gases of various kinds. Smaller planets like Earth have weaker gravity and tend to lose their primordial hydrogen atmospheres over time, ending up with secondary atmospheres formed from outgassing of their rocky interiors. Larger planets retain their primordial hydrogen and grow into gas giants. In between, in the size range of sub-Neptunes, are planets that may have retained substantial hydrogen envelopes without becoming full gas giants. If such a planet also has water, the water might exist as a deep ocean beneath the hydrogen atmosphere, kept liquid by the right combination of stellar heating and atmospheric pressure. The Hycean configuration, in other words, is a natural prediction of planet formation theory for objects in the right size range. The second argument is about the habitable zone. For an Earth-like planet with a thin atmosphere, the habitable zone is narrow. The planet has to sit at just the right distance from its star for liquid water to be stable on the surface. Move the planet a bit closer and the water evaporates. Move it a bit farther and the water freezes. For a Hycean world, the habitable zone is much wider because the thick hydrogen atmosphere acts as a strong greenhouse layer, keeping the underlying water liquid even when the planet is significantly farther from the star than Earth-like habitability would allow. Conversely, the same atmospheric pressure can also keep water liquid when the planet is closer to the star than usual, because the increased pressure raises the boiling point. The Hycean configuration, in other words, expands the territory where habitability is possible. The third argument is about observational accessibility. When you do transit transmission spectroscopy on a planet, the depth of the spectral features you can detect depends on the scale height of the planet's atmosphere. Scale height in atmospheric science is the vertical distance over which the atmospheric pressure drops by a factor of E, the mathematical constant. Scale height is proportional to temperature and inversely proportional to the mean molecular weight of the atmosphere. A hydrogen-dominated atmosphere has a much lower mean molecular weight than a nitrogen-oxygen atmosphere because hydrogen molecules weigh much less than nitrogen or oxygen molecules. The result is that hydrogen atmospheres have larger scale heights, which means they produce much deeper transit transmission features for any given temperature. A Hycean world with its hydrogen atmosphere would have transit signals roughly an order of magnitude larger than an Earth-like atmosphere on the same planet would produce. They are, in a real sense, easier to observe. That last argument is the one that made Hycean worlds particularly interesting to a generation of exoplanet astronomers thinking about how to actually detect biosignatures in the JWST era. If you want to find life on another world, you need a planet whose atmosphere you can characterize at the level of specific molecular abundances. For Earth-like atmospheres around Sun-like stars, that level of characterization is with current technology essentially impossible. The signals are too small. The required precision is beyond JWST's capabilities. For Earth-like atmospheres around red dwarfs, the signals are larger, but the corrections for stellar activity become difficult. For Hycean atmospheres around red dwarfs, however, the signals are large enough and the geometry favorable enough that genuine atmospheric characterization becomes feasible. If Hycean worlds exist, and if they harbor life, then they are exactly the kind of target where life could plausibly be detected with current instruments. They are, in the technical phrase that Madhusudhan's team used, the most promising near-term venue for biosignature searches. That logic in 2021 was the basis for prioritizing K218b as a JWST target. The planet matched the predicted Hycean profile in size, in mass, and orbital position. If Hycean worlds existed at all, K2-18b was one of the strongest candidates. TRAPPIST. The 2021 paper also worked out what kinds of biosignature gases might be detectable in a Hycean atmosphere given the chemistry of a hydrogen-rich environment. Methane and carbon dioxide were predicted to be present in any plausible Hycean atmosphere, biological or not. Their detection would not by itself indicate life, but the additional presence of certain sulfur-bearing gases, particularly dimethyl sulfide, would be much harder to explain by abiotic processes. On Earth, dimethyl sulfide is produced almost entirely by marine plankton. There is no significant known geological source. If the same molecule appeared in the atmosphere of a planet expected to have an ocean, the inference toward biological activity would be stronger than it would be for any single component on its own. The Cambridge team further subdivided the Hycean concept into 3 variants depending on the orientation of the planet relative to its star. There are temperate Hycean worlds, where the atmospheric and oceanic conditions allow for liquid water across most of the planet's surface, similar in some respects to a hot version of Earth's tropical oceans, but spread globally. There are dark Hycean worlds, which are tidally locked planets, where the night side permanently turned away from the star hosts, the liquid ocean, while the day side is too hot for surface water. And there are cold Hycean worlds, which orbit far enough from their stars that the surface is cold, but where the thick hydrogen atmosphere keeps an underlying ocean liquid through greenhouse heating. Each subtype has different observational signatures and different implications for biological possibilities. K2-18b, given its specific orbital and physical parameters, was assigned to the temperate or warm Hycean category, with conditions that the team's model suggested would be congenial to ocean-based biology if biology were present at all. This is the prediction that Madhusudhan's team was testing in 2023. They were not just looking at K2-18b's atmosphere with a generic interest. They had a specific theoretical model based on the Hycean hypothesis that predicted what the data should look like if K2-18b were a Hycean world with biological activity. They were in effect asking the planet a question, and the question had a fairly specific predicted answer. I want to step back here and say something about the larger frame this hypothesis sits in, because I think it is one of the more interesting aspects of the whole story. For most of the history of biosignature thinking, the implicit model has been Earth. We look for planets that resemble Earth in size, in temperature, in atmospheric composition, and we ask whether life might exist on them under conditions similar to Earth's conditions. That is a reasonable approach, given that Earth is the only confirmed inhabited planet we know of. But it is also a sample size of 1. Earth might be unrepresentative. The conditions for life elsewhere might differ from Earth's conditions in ways that, if we limit our search to Earth analogues, we will systematically miss. The Hycean hypothesis is one attempt to widen the search. It says that planets very different from Earth with hydrogen atmospheres and global oceans might also support life. If they do, then the typical inhabited world in the galaxy might look nothing like Earth, and our search strategy focused on Earth analogues might be looking in the wrong places. Hycean worlds, if they exist as a category, are common enough that they could be the dominant biosphere type in the universe. We just do not know yet because we have not detected any of them with confidence. Other widening proposals exist alongside the Hycean idea. There are scientists who think life might be possible in subsurface oceans on icy moons of gas giants like Europa, or Enceladus in our own solar system, or analogous moons in other systems. There are scientists who think life might be possible in the thick atmospheres of gas giants themselves, in floating layers of cloud where temperatures and pressures are mild. even though the surface far below is hostile. There are scientists who think life might be possible in liquid methane, as on Saturn's moon Titan with biochemistry, quite different from the water-based biochemistry of Earth. None of these proposals has been confirmed. All of them are plausible enough to be taken seriously by working researchers. Each represents a way of expanding the search beyond the Earth analog model. The Hycean hypothesis in this broader context is one of several attempts to think more carefully about what might count as a habitable environment. It is not a claim about how life actually arises on Hycean worlds or about what such life would look like. The hypothesis is instead a claim about which planets are worth studying carefully and what kinds of atmospheric signatures we should be looking for given the limits of current instruments. As of 2026, no Hycean world has been confirmed to exist. K2-18b is the leading candidate, but the case is contested. Other candidate Hycean worlds are also being studied. The category, if it exists at all, is still in its observational infancy. What the hypothesis has accomplished, regardless of its eventual fate, is to focus attention on a specific set of planets that are particularly well suited to atmospheric characterization with JWST. That focus has produced data. The data has produced both genuine discoveries and ongoing arguments. The arguments themselves are an indication that the field is doing the work seriously, weighing the evidence carefully, and not converging on a conclusion before the conclusion is warranted. There is another thing to acknowledge here, which is that the Hycean hypothesis itself has been challenged on technical grounds by other scientists, separate from the question of whether biosignatures have been detected on K2-18b specifically. Researchers including Nicholas Wogan at NASA Ames and Oliver Shortall at Cambridge have published work arguing that the observed atmospheric signatures of K2-18b might be explainable without an ocean at all. The planet might be a so-called gas dwarf with a thick hydrogen atmosphere over a rocky and icy interior, but no actual liquid ocean at any depth. Or it might have a magma ocean rather than a water ocean, with the water effectively bound up in molten rock at the planet's interior. These alternative models, for various reasons we will get into in a later section, fit some aspects of the observed data and have their own theoretical motivations. The Hycean interpretation, in other words, is not the only interpretation of K2-18b's bulk properties, even before the question of biosignatures comes into play. For now, what matters is this. By 2023, the Hycean hypothesis was on the table. K2-18b was the leading candidate. The Cambridge team had specific predictions for what JWST should find if their hypothesis was right, and JWST was about to look at the planet for the first time. That observation, when it came, would set off the chain of events that has occupied much of the exoplanet community ever since. The first JWST observations of K2-18b are where the modern phase of this story really begins. The data arrived, the team analyzed it, and the first paper was written. And the headlines around the world declared that something interesting had been found in the atmosphere of a small reddish star's habitable zone companion, 124 light-years from Earth. What that something actually was, the data could not yet say with confidence. But the prospect was enough to put K2-18b on the front page of newspapers across multiple continents. The 2023 JWST observation of K2-18b was carried out using both the NER spec and MIRI instruments, covering a range of near-infrared wavelengths from roughly 0.7 of a micron out to about 5 microns. This is the wavelength range where many of the most diagnostic molecular features in cool planetary atmospheres show up. water vapor, methane, carbon dioxide, ammonia, and a number of other potentially interesting gases all have detectable absorption signatures in some part of this range. Madhusudhan's team requested the observation specifically because they wanted to push their Hycean models against actual atmospheric data, and the near-infrared was the right place to start. The observations themselves consisted of monitoring the brightness of K2-18 across many wavelengths during transits of K2-18b, along with comparable monitoring outside transit. The transit duration is roughly 3 hours given the planet's orbital period and the geometry of its passage in front of its star. JWST observed several transits, gathering enough data to average down some of the random noise and produce a single combined transmission spectrum representing the planet's atmospheric absorption signatures across the observed wavelength range. The data reduction process for transit transmission spectroscopy is, even in good conditions, a substantial technical undertaking. Raw data from JWST's instruments has to be calibrated for instrumental effects, corrected for thermal drifts in the optics processed through models of the stellar spectrum, to subtract the unchanging stellar component, and then carefully analyzed to extract the small atmospheric signatures. There are typically several different data reduction pipelines that any given research group can use, each making slightly different choices about how to handle the various corrections, and the spectra they produce can differ in small but sometimes important ways. The Cambridge team used multiple independent pipelines and cross-checked their results to make sure the conclusions did not depend on any single pipeline's specific choices. The first paper from the 2023 observations appeared in the Astrophysical Journal Letters, with Madhusudhan as lead author and several Cambridge colleagues, plus collaborators at other institutions as co-authors. The paper reported 3 main findings. The first finding was the detection of methane in K2-18b's atmosphere at a statistically robust level. Methane has strong absorption features in several near-infrared bands, and the spectrum showed clear signatures of those features at the expected wavelengths. The detection significance was high enough that the methane result was not seriously contested by anyone in the subsequent reanalysis literature. K2-18b has methane in its atmosphere. That is, by current understanding, an established fact. The second finding was the detection of carbon dioxide, also at a statistically robust level, again, with clear absorption features at the expected wavelengths. The carbon dioxide detection has been somewhat more contested by later reanalyses than the methane detection, but it is still considered probable by most of the working groups looking at the data. K2-18b probably has carbon dioxide in its atmosphere. The third finding was the much more tentative one. The Cambridge team's atmospheric retrieval pipeline returned a small statistical preference for the inclusion of dimethyl sulfide, the sulfur-bearing biosignature gas, at a confidence level of about 2 sigma. 2 sigma in physics is not a detection. It corresponds to roughly a 5% probability that the apparent signal is just statistical noise. 2 sigma signals come and go in scientific data all the time without representing real detections of anything. The Cambridge team described their result as a tentative inference rather than a detection. They emphasized that more data would be needed before any claim about dimethyl sulfide could be made firmly. They published the tentative inference openly in the literature with the appropriate caveats about its statistical significance. What gave the tentative inference its weight, however, was not the statistics in isolation. It was the context. Methane and carbon dioxide were both predicted by the Hycean hypothesis. Dimethyl sulfide was also predicted by the Hycean hypothesis if the planet hosted biological activity. The pattern of detections, even at the levels of confidence achieved in 2023, was consistent with the predictions of a Hycean with life model. The pattern was also consistent, of course, with several other models that did not invoke life. The data alone could not distinguish among the possibilities, but the combination of the robust methane and carbon dioxide detections with the tentative dimethyl sulfide signal was enough to make K2-18b an extremely high priority target for follow-up. I want to spend some time on dimethyl sulfide itself, because the molecule is genuinely interesting in ways that deserve attention beyond its role as a biosignature candidate. Dimethyl sulfide, abbreviated DMS, is a compound with a chemical formula C2H6S. It has 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom arranged with 2 methyl groups attached to the sulfur. It is a small, simple molecule. It is also one of the most ecologically significant trace gases in Earth's atmosphere. On Earth, DMS is produced in vast quantities by marine phytoplankton, the microscopic algae that drift through the upper layers of the world's oceans. The phytoplankton make a precursor compound called dimethyl sulfoniopropanate, often written as DMSP, which serves various physiological functions inside the cell. When the phytoplankton are eaten or stressed, or break down, the DMSP is converted into DMS, which then escapes from the seawater into the atmosphere. The total amount of DMS produced this way is substantial. Marine phytoplankton release something like 20 million tons of sulfur per year into the atmosphere in the form of DMS. That is the dominant biological sulfur flux on Earth. The phytoplankton themselves are tiny, mostly invisible to the naked eye, but the cumulative effect of trillions upon trillions of them, all releasing their small contributions across the global ocean, adds up to a planetary-scale chemical signature that, in principle, an alien astronomer with the right instruments could detect from across interstellar space. That is the kind of signal that the K2-18b observations have been searching for in a different planet's atmosphere with our own, much earlier generation instruments. What DMS does once it reaches the atmosphere is also worth noting, because it makes the molecule more than just a passive biosignature. DMS is oxidized in the upper atmosphere into sulfate aerosols, which serve as cloud condensation nuclei. The sulfate particles attract water molecules and seed the formation of cloud droplets. More DMS in the atmosphere means more cloud condensation nuclei, means more clouds means more reflected sunlight, which can affect the climate. Some atmospheric scientists have argued that DMS production by phytoplankton constitutes a kind of planetary-scale biological feedback on Earth's climate, with marine ecosystems modulating their own light environment by adjusting the rate at which they release this volatile sulfur compound. The full picture is complicated and debated, but the basic point is that DMS is not just a passive biosignature. It is a participant in Earth's atmospheric chemistry and climate system. For the purposes of biosignature science, what matters is that DMS on Earth has essentially no significant abiotic source. Volcanoes do not produce it in meaningful quantities. Lightning does not make it. Ordinary photochemistry of common atmospheric gases does not generate it. The pathway from phytoplankton to atmospheric DMS is the dominant pathway by a wide margin. If DMS is detected in the atmosphere of an exoplanet at concentrations comparable to those on Earth, the most natural inference is biological activity, because no plausible abiotic mechanism is known to produce the molecule in those quantities. The phrase "no plausible abiotic mechanism is known" is doing important work in that sentence. It does not say that no abiotic mechanism exists. It says that no abiotic mechanism is currently known. The history of astrobiology is full of cases where a molecule once thought to be biological was later shown to have abiotic sources under the right conditions. Methane is the classic example. For decades, atmospheric methane was treated as a strong potential biosignature, until detailed work showed that volcanic and hydrothermal processes can produce methane in significant quantities under planetary conditions. Methane is now classified as a weak biosignature, useful in combination with other markers, but not sufficient on its own. DMS could turn out to be the same kind of story. Some recent work by researchers, including Nora Hani and colleagues at the University of Bern, has detected DMS in comets in our own solar system where there is no possible biological source. The cometary DMS appears to be produced by photochemistry of more complex organic molecules in the comet's icy nucleus, exposed to ultraviolet radiation from the Sun. Other recent work has detected DMS in interstellar gas clouds, where again, no biology is involved. These detections do not invalidate DMS as a potential biosignature, but they do complicate the picture. Under conditions different from Earth's DMS, can be produced abiotically. Whether the conditions on K2-18b favor or disfavor abiotic DMS production is itself an open question. This is the larger lesson that biosignature science has slowly absorbed over the last several decades. There is no single molecule that by its presence alone proves the existence of life. Every candidate biosignature has potential abiotic sources under the right conditions. What you really need to make a serious case for life is a combination of features that together are difficult to explain without invoking biology. Multiple gases in disequilibrium with each other. The gases at concentrations that fit known biological processes better than they fit known abiotic ones. Independent confirmation by multiple instruments and multiple teams. Ruled out alternatives across the relevant chemistry. The standards of evidence framework that the astrobiology community has been developing over recent years tries to formalize this kind of layered case building. Single molecule detection, even at high statistical significance, is not enough. The disequilibrium argument deserves a moment of its own because it is one of the more elegant ideas in modern biosignature theory. The basic insight goes back to early work by James Lovelock in the 1960s and was carried forward by various researchers, including Carl Sagan, in the decades that followed. The idea is this. Many gases, when present together in an atmosphere, will react with each other given enough time and the right conditions. Methane and oxygen, for example, will react to produce carbon dioxide and water. If you find an atmosphere with both methane and oxygen present in significant quantities, something is continuously replenishing one or both of them because the reaction would otherwise drive the concentrations down to nearly nothing over geological time. On Earth, biology is what keeps both methane and oxygen in the atmosphere by producing methane in wetlands and ruminant guts, and producing oxygen through photosynthesis. The two gases in their persistent disequilibrium are a signature of an active biosphere. A planet without life would not maintain that disequilibrium because nothing would replenish the reacting components fast enough to balance the reaction. For K2-18b, the relevant disequilibrium argument is more subtle than the methane-oxygen case because the planet's atmosphere is hydrogen-dominated rather than oxygen-dominated. But the same general logic applies. Combinations of gases that are out of chemical equilibrium with each other point towards sources that can refill them faster than the equilibrium reactions can deplete them. Biology is one such source. Active geology, particularly volcanism, is another. The trick in interpretation is figuring out which source is more consistent with the specific combination of gases observed. In 2023, with the first JWST observations in hand, the K2 or 18b case did not yet meet that bar. The methane was solid. The carbon dioxide was probable. The DMS was at 2 sigma, which is below detection threshold, even before considering the question of biological versus abiotic origin. The team published the results honestly, with all the appropriate caveats. The headlines, predictably, were less careful than the paper. Various media outlets treated the tentative DMS inference as if it were a confirmed detection of a biosignature. The Cambridge team itself did not make any such confirmed claim, but the overall narrative in the public sphere was substantially more confident than the data warranted. What followed within the scientific community was a normal next step. Other researchers requested follow-up observations. JWST scheduled additional time on K2 18b this time with the MIRI instrument, which would provide a different wavelength range and an independent test of the dimethyl sulfide signal. The MIRI observations would not be available until 2025. Until then, the 2023 results sat in the literature as a tentative case for an interesting atmospheric composition with the dimethyl sulfide question explicitly flagged as awaiting further data. That further data, when it arrived, would not settle the question. It would instead transform the discussion in ways that nobody on the Cambridge team had anticipated. The MIRI observations of K2 18b, taken in early 2024 and analysed through the following year, would produce a paper whose interpretation became the most contested single result in modern exoplanet science. The MIRI observations of K2 18b were carried out in early 2024 as part of JWST's General Observer Program 2722, with Madhusudhan listed as principal investigator. The observations used MIRI's low-resolution spectrometer in the slitless prism configuration covering the wavelength range from about 6 microns to about 12 microns. This range is deliberately complementary to what ENEA-SPEC and NIRIS had observed in 2023. The spectral features expected from dimethyl sulfide and from a related sulfur-bearing molecule called dimethyl disulfide both show up most strongly in the mid-infrared, particularly in the 8 to 11 micron range. If those molecules were present in K2 18b's atmosphere at the levels suggested by the 2023 hint, the MIRI data should be able to confirm or refute the inference at higher confidence than the near-infrared data alone could provide. The data was taken. The Cambridge team spent most of the following year analysing it. The analysis pipeline involved many of the same steps as the 2023 work, but applied to MIRI rather than ENEA-SPEC or NIRIS. Different instrumental systematics, different stellar contamination corrections, different choices about how to bin the spectrum into the wavelength channels used for the atmospheric retrieval. By April of 2025, the team's analysis was complete, and on April 17th, the paper appeared in the Astrophysical Journal Letters, with the title New Constraints on DMS and DMDS in the Atmosphere of K2-18b from JWST MIRI. The lead author was Madhusudhan, with Savas Konstantinou-Mans Holmberg, Subhajit Sarkar, Anjali Piete, and Julianne Moses as co-authors. The headline result was a 3 sigma detection of features consistent with dimethyl sulfide and/or dimethyl disulfide in the MIRI spectrum. 3 sigma corresponds to roughly a 0.3% probability that the signal arose by chance. The paper noted that the 2 molecules have overlapping spectral features in the wavelength range observed, so distinguishing between them with the current data was not yet possible. But the inference of at least one of the 2 the team argued, was statistically supported by the data. The paper also estimated the abundance of the inferred molecule, finding that if dimethyl sulfide were the source, its concentration in K2-18B's atmosphere would have to be more than 10 parts per million by volume. That is roughly 10,000 times higher than the typical concentration of dimethyl sulfide in Earth's atmosphere, which sits at less than 1 part per billion. The Cambridge team noted that the elevated concentration was consistent with their predictions for a Hycean world, with substantial biological activity. The same prediction had been worked out theoretically in earlier papers before the MIRI data was available. The data in the team's reading fit the prediction. In their interpretation section, the team wrote that the most natural explanation for the observed signal, taken together with the methane and carbon dioxide detections from 2023, and with the predicted properties of a Hycean ocean world, was biological activity. They were careful to note that more data would be needed before any firm claim about life could be made. They emphasized that the 3 sigma confidence level was below the 5 sigma threshold typically required for definitive claims in physics, but they presented their result as the strongest hint yet of biological activity outside our solar system, and the headlines that followed reflected that framing. The headlines were everywhere within hours. Major outlets ran with phrases like strongest hints of life and biosignature gases detected. NASA notably did not issue an accompanying press release endorsing the result. The space agency's restraint was itself a small signal. When NASA does not weigh in on what would be one of the most consequential scientific findings in human history, the silence is meaningful. Within days, the response from the broader exoplanet community began to arrive. The first responses were not formal papers. They were comments on social media blog posts, statements from individual scientists at conferences and in interviews. The general tone was caution, with several specific concerns surfacing repeatedly. Sarah Seeger, a professor of planetary science at MIT and one of the foundational figures in modern biosignature theory, gave several public statements emphasizing that any single biosignature gas, no matter how suggestive, is not sufficient evidence for life. Seeger has spent decades thinking about what would actually constitute a defensible claim of biosignature detection on an exoplanet, and her position has been consistent. The bar is high. The alternative explanations need to be ruled out one by one, and no single instrument or single team can produce a result definitive enough on its own. Her response to the K2-18b claim was not to declare it wrong. It was to apply the standards she had been arguing for over years. The claim, she said, in effect did not yet meet those standards regardless of how interesting the data was. Within a few weeks, the first formal pushback papers began appearing. In late April and through May of 2025, several preprints went up on the Kharkiv physics preprint server, each from a different group, each questioning the statistical foundations of the Cambridge team's claim from a different angle. Jake Taylor, working at the University of Oxford, posted a preprint focused specifically on the statistical methodology of the MIRI analysis. The Cambridge team had reported a 3.4 sigma rejection of a flatline model in favor of their preferred 16-parameter atmospheric model. Taylor's analysis pointed out that this comparison was not a strict nested model test, because the flatline model was not a subset of the 16-parameter model, and that more careful Bayesian comparisons of the two models, accounting for the prior parameter ranges, gave weaker support for any specific molecular detection. Taylor also tested simpler Gaussian feature fits to the data, asking whether the spectrum showed evidence of any spectral feature at all, and found that the apparent features were modest, and could be fit equally well by a variety of small bumps that did not specifically correspond to dimethyl sulfide. Soon after, a paper by Louise Wellbanks at Arizona State University and Matthew Nixon at the University of Maryland appeared taking a different angle on the same question. Wellbanks and Nixon's analysis focused on the choice of wavelength binning in the MIRI data reduction. They pointed out that the apparent features in the spectrum were sensitive to how the data was binned, and that with their preferred binning approach, 87.5% of retrievals using the same model framework did not favor the presence of dimethyl sulfide or dimethyl disulfide. They concluded that the apparent detection was substantially less robust than the original paper had presented, and that the choice of binning had been a hidden but important driver of the result. The implication was not that the Cambridge team had done anything dishonest. It was that the methodology involved choices that made differently would have produced a different answer. These early pushback papers were rapid by the standards of academic publishing. The R of preprint system allows scientists to circulate work in progress before formal peer review, and in fast-moving controversies, it serves as the de facto venue for real-time exchange. The Cambridge team had access to the same R to Kirchhoff system, and they responded with comments, additional analyses, and further methodological clarifications. The discussion was unfolding in public in something close to real time, with each side updating its arguments as the other side produced new analyses. I want to spend a moment on what 3 sigma actually means in scientific practice, because the public framing of the K2-18b result tended to treat the number as more significant than it really is. 3 sigma is, in pure statistical terms, a result that has roughly a 0.3% probability of arising from random noise alone, given a specific null hypothesis. In particle physics, the standard for claiming a discovery is 5 sigma, which corresponds to a 1 in roughly 3.5 million chance of being noise. The 5 sigma threshold was adopted partly because of historical experience with 3 sigma results that turned out to be wrong. There are many ways for a 3 sigma result to be misleading, including unaccounted for systematic errors, the so-called look elsewhere effect, when you search many possible signals and find one by chance, and the sensitivity of the result to specific analysis choices. The 5 sigma standard was meant to mostly rule out these false positive scenarios. For exoplanet atmospheric work, the field has not strictly settled on a sigma threshold for biosignature claims, in part because the question is so new. 3 sigma detections of methane on exoplanets are routinely reported and accepted in the literature. 3 sigma detections of biosignature gases on exoplanets, however, raise more concern because the claim being made is so much larger. The same statistical confidence carries different implications depending on what the result is being used to argue. This was, in a sense, the deepest issue in the early pushback against the Cambridge team's MIRI paper. The data showed something at 3 sigma. Whether that something was specifically dimethyl sulfide, whether it represented evidence of biological activity, and whether the underlying signal was robust against changes in the analysis methodology, were all separate questions that required separate evaluation. The Cambridge team had presented a coherent answer that connected all of these questions through their Hycean framework. The pushback teams were in effect asking whether the connections were as tight as the Cambridge presentation made them seem. Their answer in early 2025 was that the connections were looser than they appeared. Sarah Seeger's broader point in her public statements was about the role of independent confirmation in biosignature science. A single result from a single team, even at high statistical significance, is not how the scientific community typically converges on far-reaching claims. Independent confirmation by separate teams using separate analyses, ideally with separate instruments, is what ultimately establishes whether a result is real. The K2-18b result in 2025 did not yet have that confirmation. The data was public, the analyses were unfolding, but the convergence had not yet happened. There is an additional layer worth pointing out about what the public conversation looked like in those first weeks. Major media outlets in many cases ran headlines that conflated the 3 sigma signal with confirmation of life. Some headlines specifically used phrases like "scientists detect life on distant exoplanet," or variants that the actual paper did not support. Madhusudhan and his co-authors in interviews repeatedly pushed back against that framing, emphasizing that more data was needed and that the 3 sigma threshold was below the level normally required for a definitive claim. The Cambridge press release itself was more careful than many of the headlines it inspired. But the gap between the published paper's careful caveats and the popular press treatment of the result was substantial, and the overall public impression in spring of 2025 was that life had been detected, even though no scientist involved in the original work was making that claim. This pattern, where a careful scientific result gets amplified into something more confident in the popular discussion, is not unique to the K2-18b case. It is a recurring feature of how astronomical results, particularly results with implications for the search for life, get communicated to broader audiences. The science press has its own incentives to produce striking headlines. Search-based content algorithms reward strong claims over careful ones, and the public understandably finds confident statements more interesting than nuanced ones. The result is that biosignature claims tend to get inflated as they move outward from the original paper, with each level of communication adding a bit more confidence than the previous level had warranted. By the time the claim reaches the average reader, the original 3 sigma tentative inference has often turned into a confirmed detection in the popular framing. The Reanalysis teams, in some sense, were responding not just to the Cambridge paper, but to the broader public misframing of what the paper actually said. Their work was an attempt to slow the inflation, to put the methodological caveats back into the discussion, to remind the field and the public that biosignature claims require careful evidence, and that no single paper, no matter how well done, is sufficient to establish them. This is the service the Reanalysis teams were performing, and it is one of the reasons their work deserves to be treated as serious science rather than as obstruction. What was clear, though, was that the discussion was now far beyond a simple question of whether the Cambridge team had found life. The question was whether the spectrum even contained the features they thought it contained regardless of biology. That question, in turn, depended on choices in data reduction and statistical modeling that different teams were making differently. The argument was not about astrobiology in the first instance. It was about the underlying analysis. The astrobiological implications would only matter once the analysis questions were settled and the analysis questions were genuinely open. That is the state in which the most important reanalysis paper by Raphael Luque and his collaborators at the University of Chicago would arrive a few months later. That paper, when it came out in August of 2025, would be the most thorough independent attack on the Cambridge result yet attempted, and its conclusions would shape the public discussion of K2-18b for the rest of the year. The most thorough single reanalysis of the K2-18b data appeared in Astronomy and Astrophysics in August of 2025, with Raphael Luque, a postdoctoral researcher at the University of Chicago, as lead author. The full paper title was Insufficient Evidence for DMS and DMDS in the Atmosphere of K2-18b, from a joint analysis of JWST nearest near-spec and MIRI observations. The framing was already in the title. The team had analysed the same publicly available JWST data that the Cambridge group had analysed, brought the near-infrared and mid-infrared observations together into a single joint analysis instead of treating them separately, and concluded that the evidence for the contested biosignature gases was not statistically robust when the full dataset was considered as a whole. Let me walk through what the Luca paper actually did, because the methodology matters. The team applied an atmospheric retrieval code called Platon, which is a publicly available GPU-accelerated software tool that has been used in many JWST exoplanet atmospheric studies. Platon has its own implementation of the same general physics that the Cambridge team's pipeline implements, but with different choices about how the molecular line lists are handled, different opacity calculations, and different priors on the various model parameters. Different code, in other words, encoding the same physics in slightly different ways. The point of using a different retrieval framework was not to reproduce the Cambridge team's analysis exactly. It was to ask whether the conclusions held up when the analysis choices were varied. The team also took a key methodological step that the Cambridge MIRI paper had not taken. They analysed the near-infrared NIRIS and NIRSPEC data, together with the mid-infrared MIRI data, in a single joint retrieval. The Cambridge team's MIRI paper had focused primarily on the MIRI data alone, treating it as an independent test of the dimethyl sulfide signal. The Luca paper argued that this was the wrong approach. If the planet has an atmosphere, the same atmosphere should produce consistent signatures across the entire wavelength range observed by JWST. Any model that fits the MIRI data must also fit the NIRSPEC and NIRIS data. Doing the analysis on MIRI alone, without checking consistency, with the near-infrared risks finding spurious features that do not actually correspond to atmospheric components present at the level required to fit the full dataset. When Luca and his colleagues did the joint analysis, the picture changed. The methane detection survived intact. The carbon dioxide detection survived, though with somewhat reduced confidence compared to the original Cambridge analysis. The dimethyl sulfide and dimethyl disulfide signals, however, did not survive at any statistically meaningful level. The team found that the apparent features in the MIRI spectrum that the Cambridge team had attributed to those molecules could be fit equally well by other molecules, including ethylene, which has overlapping absorption features in the same wavelength range. The paper specifically noted that the presence of dimethyl sulfide and ethylene was in their analysis interchangeable. The same MIRI data could be explained by either, and the choice between them was not determined by the data itself, but by the priors and assumptions imposed by the analysis framework. The paper's conclusion, stated directly in its title, was that the evidence for dimethyl sulfide and dimethyl disulfide was insufficient when the full JWST dataset was analysed jointly. The team did not claim that the molecules were definitely absent from the atmosphere. They only claimed that the data did not support a confident detection. The data was in their reading consistent with a hydrogen-rich atmosphere containing methane and probably carbon dioxide, but not requiring any sulfur-bearing biosignature gas at all. There was also a separate paper that had appeared earlier in early 2025 by Stephen Schmidt and a large team of collaborators, including researchers at Johns Hopkins, the University of Michigan, and St. Andrews. That paper had reanalyzed the 2023 NIRIS and NIRSPEC data using yet another atmospheric retrieval framework and had reached similar conclusions. Methane was robustly detected. Carbon dioxide and dimethyl sulfide were not statistically supported. The Luca paper cited the Schmidt result alongside the Taylor and Wellbanks-Nixon analyses as part of a converging picture from multiple independent teams that the original biosignature claims were not robust. The Lucke paper itself made several specific methodological points worth understanding, because they illustrate the kinds of choices that turn out to matter in spectral analysis at the edge of detectability. First, the team used opacity tables generated from the DACE database at much higher spectral resolution than the default Platon opacities provide. The opacities are the basic physical ingredients that tell the retrieval code how strongly each gas absorbs at each wavelength. Higher resolution opacities, the team argued, are necessary when the data being fit comes at the native instrumental resolution of NIRIS and NIRSpec. Lower resolution opacities can introduce small systematic errors that, while individually negligible, can add up to misleading molecular detections in the final retrieval. Second, the team halved the temperature spacing of the opacity grid from 100 Kelvin to 50 Kelvin. K2-18b is by exoplanet standards a relatively cold target, and the standard opacity grids that work well for hot gas giants do not interpolate cleanly to the temperatures involved in cooler atmospheres. The finer temperature spacing matters for getting the absolute absorption strengths right at the planet's actual atmospheric temperatures. Third, for methane specifically, the team used the high-temp 2020 line list rather than the more commonly used exomol line list. The high-temp list, the paper noted, covers the full wavelength range spanned by the nearest data, while the exomol list has gaps in coverage that can cause artifacts in retrievals at the affected wavelengths. The choice of methane line list, in other words, can affect the final result, and different teams making different choices can get different answers. These methodological details are not glamorous. They will not appear in any popular write-up of the K2-18b debate, but they are the kind of details that, in modern atmospheric retrieval work, end up determining whether a particular molecular detection is real or whether it is an artifact of the analysis choices. The Lucke paper went to considerable lengths to document and justify each methodological choice in order to make the reanalysis as transparent and reproducible as possible. The argument the paper was making, in effect, was that when you make these specific defensible choices, the dimethyl sulfide signal disappears. What followed the Lucke paper in the second half of 2025 was a continued back and forth. Madhusudhan and his team responded with additional analyses defending their interpretation, arguing that the Cambridge methodology was sound and that the Reanalysis team's choices were the ones introducing problems. The Reanalysis teams responded with further work showing that the methodological concerns persisted across various reasonable choices. Wellbanks in interviews was quoted as saying that the Cambridge team's response did not address the underlying statistical concerns, and that further claims based on the same flawed framework would not change the conclusion. Madhusudhan also in interviews maintained that his team's interpretation remained the most natural reading of the data, and that the standards of evidence being demanded by the reanalysis teams would, if rigidly applied, prevent any biosignature claim from ever being made on any planet. This was on both sides a serious scientific argument. Neither team was acting in bad faith. Both teams were using publicly available data and well-established methods. The disagreement was about which methodological choices were appropriate and about how much confidence the data could support given the full set of choices that needed to be made. I want to step back here and address something that often gets lost in popular coverage of this kind of dispute. The reanalysis teams are not skeptics blocking a discovery. They are also not crusaders against the Cambridge team. They are working scientists doing exactly what science requires. When a major claim is made, especially a claim with implications as large as detecting life beyond Earth, other scientists are obligated to scrutinize it carefully. They are obligated to use the same data and apply alternative analyses. They are obligated to publish their results even when those results challenge a prominent paper. This kind of independent scrutiny is not a hostile act. It is the basic operation of how scientific knowledge gets sorted from scientific noise. If the Cambridge team's result is correct, then over time, as more data accumulates and as more independent analyses are done, the result should become more robust, not less. If the result is not correct, then the same accumulating evidence should reveal that. Voiscan. The fact that the K2-18b case has not yet converged in either direction is informative. It tells us that the data as it currently stands is genuinely ambiguous, and that any confident interpretation in either direction is going beyond what the evidence supports. There is another layer to this story that needs to be added before we move on, because it complicates the picture in a different way. While the dimethyl sulfide debate has been unfolding around the spectroscopic data, a separate group of scientists has been challenging the Hycean hypothesis itself on entirely different grounds. The challenge does not concern whether dimethyl sulfide is present in K2-18b's atmosphere. It concerns whether K2-18b actually has an ocean at all. The leading voices in this challenge are Oliver Shortall, a planetary scientist at Cambridge, and Nicholas Wogan, a researcher at NASA Ames Research Centre. Both have published independently and in collaboration with others, arguing that the bulk properties of K2-18b, the size, the mass, the density, can be explained by planetary models that do not involve a global liquid water ocean. The alternative model is sometimes called a gas dwarf, sometimes a mini Neptune, sometimes a magma ocean world, depending on the specific variant being proposed. The basic idea is that K2-18b might have a thick hydrogen atmosphere over a rocky and icy interior, with the water effectively bound up in the deep mantle rather than sitting as a surface ocean. Or, in another variant, the planet might have a global magma ocean with rock so hot that it is molten beneath the hydrogen atmosphere. In neither case would there be a surface ocean of the kind the Hycean hypothesis envisions. The arguments for these alternative models come from detailed geochemical calculations of how K2-18b's interior would equilibrate over time, given its size, mass, age, and likely composition. Shortall's analyses suggest that the abundances of certain expected atmospheric components like ammonia are not what you would expect from a Hycean ocean world, but are consistent with a gas dwarf or magma ocean alternative. The atmospheric chemistry on these models would be dominated by interactions between the hydrogen atmosphere and the underlying hot rock, rather than by a surface ocean and any biology that might inhabit it. The Cambridge team has responded to these challenges as well, arguing that the gas dwarf and magma ocean models do not in fact fit the observed atmospheric composition, as well as the Hycean model does, particularly when the methane to ammonia ratio and the carbon dioxide to carbon monoxide ratio are both considered. The geochemistry-based debate is in some ways more technical and less publicly visible than the dimethyl sulfide debate, but it has similar structural features: same observed data, different interpretive frameworks, different conclusions about what the planet actually is. The combined effect of all these challenges is that as of early 2026, the picture of K2-18b is genuinely unsettled at multiple levels. We do not yet know whether the planet has a liquid water ocean. We do not yet know whether dimethyl sulfide is present in its atmosphere at any significant level. We do not yet know whether the atmosphere is fully consistent with a Hycean configuration or with one of several alternative configurations. And we certainly do not know whether the planet hosts life. What we do know with reasonable confidence is that K2-18b has methane in its atmosphere, that it almost certainly has carbon dioxide, that it sits in the habitable zone of its red dwarf star, that it has a relatively low bulk density, implying significant volatile content, and that it remains the most carefully studied, potentially habitable exoplanet known to humanity. That last item, more than anything specific to the biosignature question, is the historically significant fact about this planet. K2-18b is the first rocky or icy world in another star's habitable zone, whose atmosphere we have studied directly with anything like the level of detail we apply to the planets in our own solar system. It is the leading edge of a new kind of astronomy. Whether it harbors life or not, it is the planet that taught us how hard the question is going to be to answer in any specific case. But K2-18b is not, of course, the only candidate. The broader field of habitable zone exoplanet atmospheric characterization extends to several other systems that JWST has been observing in parallel. Those other systems form their own important part of the story, and they help us understand what K2-18b looks like in context. The most carefully studied alternative to K2-18b in the search for habitable exoplanets is a system about 40 light-years from Earth called TRAPPIST-1. The system was discovered in 2016 by a team led by Belgian astronomer Michael Gillen, using a small ground-based telescope at La Silla Observatory in Chile. The original telescope was called TRAPPIST, which is an acronym for Transiting Planets and Planetesimals Small Telescope. The acronym was chosen partly as a tribute to the Belgian Trappist monasteries, which are famous for, among other things, their beer. The star itself was given the name TRAPPIST-1 in honor of the Discovery telescope. TRAPPIST-1 is even smaller and cooler than K2-18. It is an ultra-cool red dwarf classified as M8V, with a mass of only about 9% of the Sun, and a luminosity of roughly 0.05% of the Sun's. It is by stellar standards barely a star at all. Above a slightly lower mass threshold, the object would have failed to ignite hydrogen fusion in its core, and would instead have ended up as a brown dwarf, an object intermediate between a star and a giant planet. TRAPPIST-1 made it across the threshold, but only just. Its small size makes it relatively dim, and it is invisible to the naked eye despite being one of our closer stellar neighbors. What makes TRAPPIST-1 fascinating is the planetary system around it. The star hosts 7 roughly Earth-sized planets, all in remarkably tight orbits, all transiting their host star from our line of sight. The 7 planets in order of distance from the star are designated TRAPPIST-1b through TRAPPIST-1h. 3 of them, TRAPPIST-1d, TRAPPIST-1e and TRAPPIST-1f, sit in the habitable zone, where surface temperatures could potentially allow liquid water given the right atmosphere. The orbital periods are short, ranging from about 1.5 days for the innermost planet to about 19 days for the outermost. The whole system is, in a sense, a compressed solar system, with 7 planets crammed into a region smaller than the orbit of Mercury around our Sun. The geometric arrangement of the system is particularly favorable for atmospheric studies. The transits are deep because the planets are large compared to the small star. The transits are frequent because the orbital periods are short. The system has been one of the highest priority targets for JWST atmospheric characterization since the telescope began science operations. What JWST has actually found in its observations of the TRAPPIST-1 planet so far has been somewhat sobering for the broader hopes of the system as a habitability target. The two innermost planets, TRAPPIST-1b and TRAPPIST-1c, were observed by JWST in 2023 and 2024, with thermal emission measurements looking at the infrared light coming from the planets directly, rather than at transit transmission spectra. The thermal emission data was consistent with both planets being airless, or at least having atmospheres that are too thin to redistribute heat from the day side to the night side. TRAPPIST-1b appears to have a dayside temperature of around 500 Kelvin, which fits an airless rock with no atmospheric heat transport. TRAPPIST-1c shows similar properties. The implication, if these results hold up, is that the inner TRAPPIST-1 planets may have lost their primordial atmospheres entirely. The loss is plausibly due to the long history of stellar activity from TRAPPIST-1 itself. Ultra-cool red dwarfs are even more magnetically active in their youth than larger red dwarfs like K2-18, and the close-in planets would have been exposed to significant ultraviolet and X-ray radiation over hundreds of millions of years. Atmospheric stripping under those conditions is a real concern, and the JWST observations of the inner planets suggest that the concern was warranted. What this means for the outer planets, particularly the habitable zone trio of TRAPPIST-1 Hundi, TRAPPIST-1 Wani, and TRAPPIST-1 is not yet clear. They are farther from the star and would have experienced less intense radiation exposure than the inner planets. They might have retained their atmospheres. They might not have. The observations needed to characterize their atmospheres are still being scheduled and analyzed. As of early 2026, no firm conclusions have been published on whether any of the outer TRAPPIST-1 planets have atmospheres at all, let alone what those atmospheres might contain. The TRAPPIST-1 system, in other words, represents a different kind of test for habitability, where K2-18b is potentially a Hycean world with a hydrogen-rich atmosphere over a possible global ocean. The TRAPPIST-1 planets, if they are habitable, would be more Earth-like in their basic configuration, with thinner atmospheres and rocky surfaces. The two cases probe different parts of the parameter space of possible habitable worlds. Both are important. Both are being pursued. Neither has yet produced a confirmed detection of either life or anything like it. A third major candidate that JWST has been characterizing is a planet called LHS 1140b, located about 49 light-years from Earth in the constellation Cetus. LHS 1140b orbits its red dwarf host once every 25 days. The planet is somewhat larger than Earth, roughly 1.7 times Earth's radius and about 5.5 times its mass. It sits in its star's habitable zone with an equilibrium temperature similar to that of K2-18b. JWST observations of LHS 1140b in 2024 and through 2025 have suggested that the planet may be a water world with a possible deep ocean covered by a thinner atmosphere than the Hycean model would predict. The atmospheric characterization is ongoing, and as with K2-18b, different teams analyzing the same data have reached different conclusions about specific molecular detections. LHS 1140b is interesting for at least two reasons beyond its potential habitability. First, the host star is somewhat less active than TRAPPIST-1, making the corrections for stellar activity in the transit data simpler than for the TRAPPIST system. Second, the planet's bulk density suggests that it has a substantial rocky and water composition rather than a thick hydrogen envelope, which would put it in a different category from K2-18b's possible Hycean configuration. If LHS 1140b is genuinely a water world with a thin atmosphere, it would be one of the closest analogues in the known exoplanet catalogue to certain theoretical proposals for habitable worlds with conditions roughly similar to a wetter version of Earth. The contrast between K2-18b and LHS-1140b is itself worth holding in mind, because it points to a methodological question that the field is still working through. K2-18b on the Hycean reading is a planet whose surface conditions might be quite different from Earth's, with a deep ocean beneath a hydrogen-rich atmosphere and pressures and temperatures unlike anything in our own solar system. LHS 1140 on the Waterworld reading might be much closer to a wetter Earth, with a more familiar configuration of liquid surface water beneath a thin secondary atmosphere. Either kind of planet could in principle host life, but the kind of life each could host might be very different, and the kind of biosignatures we should look for in each case might also be different. The framework for biosignature detection that works for an Earth analog will not necessarily transfer cleanly to a Hycean world, and the framework for a Hycean world might miss biological activity on an Earth analog. The field is in real time working out what kinds of frameworks to use for what kinds of planets, and the ongoing arguments about both K2-18b and LHS-1140b are part of how that working out happens. Beyond these specific cases, there is a broader landscape of potentially habitable exoplanets that JWST has either observed already or has on the schedule for upcoming observing cycles. The total catalogue of confirmed exoplanets as of early 2026 has passed 5,800. Of those, perhaps 70 or so are in the habitable zones of their host stars, with sizes and masses small enough to be plausibly rocky or watery rather than gaseous. Of those, perhaps a dozen are close enough to Earth and have favorable enough orbital geometries that detailed atmospheric studies are feasible with JWST. The competition for JWST observing time is intense, because the telescope has many other scientific priorities, and the time allocated to exoplanet atmospheric characterization is a small fraction of the total. Each planet that does get observed becomes the focus of careful analysis and often of debate among different research teams looking at the same data. What this broader landscape tells us when you step back from any single planet is that we are in the very early days of exoplanet biosignature science. The instruments have just become capable of asking the right kinds of questions. The handful of planets that have been studied in detail are each their own special cases, with their own atmospheric properties, their own host, stars, their own observational quirks. The methodological challenges that have surfaced in the K2-18b debate are not unique to that planet. They are general features of trying to extract small atmospheric signals from noisy transit transmission spectra of distant worlds. Every new system that gets observed will produce its own version of the same set of issues. Different teams will reach different conclusions. The convergence will happen over years, perhaps decades, as more data accumulates and more instruments come online. The next generation of telescopes that will eventually take over from JWST in this kind of work is still mostly on the drawing board. The Habitable Worlds Observatory, currently in early planning stages at NASA, would be designed specifically to do direct imaging and atmospheric characterization of Earth-like planets around Sun-like stars. The extremely large telescope under construction in Chile would have certain capabilities for biosignature work even from the ground. Various other proposed missions have been discussed in the planning literature. None of these will be operational for at least a decade. JWST, in the meantime, is the only instrument we have for this kind of science, and the time pressure on its observing schedule is genuine. I want to soften the prose here because we are moving toward the latter half of this drift, and the practical details of which telescopes will come online when are not the most important thing for what we are doing tonight. What matters more is the quieter point underneath all of this technical detail. We are alive, you and I, at the moment in human history when the search for life beyond Earth has stopped being a theoretical exercise and become a real data analysis problem. People in the past dreamed about other inhabited worlds. They wrote science fiction about them. They speculated philosophically about them. They could not, until now, actually look at one of them and ask whether it was inhabited, because they did not have the instruments and they did not have the candidate planets and they did not have the methodology. We have all three, however imperfectly. The methodology is being worked out in real time in the unfolding K2-18b debate. The instruments are working. The candidates are being studied. We are right now in the thick of doing it. The question of whether we will succeed in identifying life on another world within our lifetimes is of course open. The K2-18b case might converge in either direction. The other candidates might produce surprises. New planets might be discovered that are even better targets than the ones we currently know about. Or the question might simply remain unresolved for decades, with each new piece of evidence adding to the picture without ever quite settling it. Any of these outcomes is consistent with where we currently are. None of them is precluded by the data. What we can say with reasonable confidence is that the question is now being asked in a way it has never been asked before. The data exists. The instruments are operating. The scientists are doing the careful work of weighing alternative interpretations against each other. The argument over K2-18b, despite its public messiness, is exactly the kind of argument that science needs to have when stakes are high and evidence is ambiguous. It is not a sign of dysfunction. It is a sign that the field is taking the question seriously enough to argue about it carefully. There is something quieting about that when you let it settle. We are participating, at least vicariously, in one of the more important scientific transitions in human history. The transition from speculation to data. The transition from imagining other inhabited worlds to actually examining the spectra of specific candidate worlds, one molecular feature at a time. The transition is not yet complete. The picture is not yet clear, but the work is happening in real time in laboratories and observatories scattered across multiple countries with publicly available data and publicly available analyses and publicly visible debate. You and I get to listen in from the outside as this work unfolds. That is in its quiet way a privilege. Let us hold that for a moment before we move into the closing stretch of this drift. We will not solve the K2-18b debate tonight. The professional astronomers working on it have not solved it either. What we can do is sit with the open question, with the unresolved data, with the genuine argument among careful scientists about what the evidence really shows, and let that openness be its own kind of cosmic experience. The universe is not telling us yet whether K2-18b is inhabited. The universe is, however, letting us ask the question more directly than any previous generation has ever been able to. That asking even without an answer is a real thing that is happening right now on a small planet, around an ordinary yellow star, while a smaller red star 124 light-years away continues to host a planet whose atmosphere we are still trying to understand. Let us step back all the way back and put what is happening at K2-18b in the longest possible frame. In October of 1993, a paper appeared in the journal Nature, with Carl Sagan as lead author. The full author list included W. Reed Thompson, Robert Carlson, Donald Gurnett, and Charles Hoard. The title of the paper was A Search for Life on Earth from the Galileo spacecraft. The Galileo spacecraft, on its way out to study Jupiter, had performed a flyby of Earth in December of 1990. Sagan and his colleagues had used the flyby as an opportunity to do an unusual experiment. They had pointed the Galileo instruments at our own home planet and asked, with the spacecraft's relatively modest sensors, whether they could detect that Earth was inhabited. The question was a thought experiment in the form of a real measurement. Sagan and his team wanted to know what life on a planet looks like from across the gulf of space, when the only data you have is the kind of data a passing spacecraft can collect. If we are eventually going to look for life on planets around other stars, we need to know what we are looking for, and we need to test our methodology against the only confirmed inhabited planet we have access to, which is our own. The Galileo data showed several signatures that Sagan's team interpreted as suggestive of life. There was abundant oxygen in the atmosphere, enough to be in extreme thermodynamic disequilibrium, with the methane that was also present. There was a widespread surface pigment, with a sharp absorption edge in the red part of the visible spectrum, a feature that had no obvious mineral origin and that Sagan's team interpreted as the signature of photosynthetic vegetation. The combination of these features, the team wrote, was strongly suggestive of life. They also noted that the spacecraft had picked up amplitude-modulated radio signals from Earth, which they took as uniquely attributable to intelligence. These observations taken together would have been enough for any visiting civilization to conclude that Earth was both inhabited and home to technological intelligence. The 1993 paper was a thought experiment. The Galileo team was using a real spacecraft on a real planet, but the planet was Earth, and there was no genuine question about whether Earth was inhabited. The exercise was a test of methodology. What kinds of features should you look for? What thresholds should you apply? How do you distinguish biological signatures from geological or chemical ones? The answers Sagan's team developed have been foundational for biosignature theory ever since. What is happening with K2-18b is in some real sense the same exercise applied to a real dataset, with no ground truth to compare against. We do not know whether K2-18b is inhabited. We have the spectrum, the methodology, and the alternative explanations. We have the disagreements among careful scientists about what the data actually shows. What we do not have is the ground truth. The planet either harbors life or it does not, and we cannot in any near term find out which. This is a different kind of intellectual situation than humans have ever been in before. For all of recorded history, the question of whether other planets host life was either purely speculative or very recently a question we did not yet have the tools to seriously ask. Sagan's 1993 exercise was a preparation for the moment when we would have those tools. The K2-18b debate is the first moment when we have actually started using them. The case is contested, the data is real, and the interpretation is unsettled. We are sitting right now in the historical situation that Sagan and his colleagues were preparing for 30 years ago. I find this genuinely worth dwelling on, because the historical novelty of where we are is part of what makes the K2-18b story interesting in a way that goes beyond any specific finding. For most of human history, when philosophers and theologians and scientists asked whether other worlds were inhabited, the question was abstract. There was nothing concrete to argue about. The answer might be yes, the answer might be no, but no possible piece of evidence could resolve the debate. People who believed in inhabited worlds and people who did not could have entirely different views and never have a way to test them. That has changed. Slowly over the last 30 years, the question has shifted from abstract speculation to concrete data analysis. The shift began with the 1995 discovery of 51 Pegasi b, which established that planets around other stars exist immeasurable numbers. It continued through the Kepler mission, which showed that small habitable zone planets are common across the galaxy. It has now reached a point where individual candidate worlds like K2-18b are being studied in atmospheric detail with instruments capable of detecting specific molecular signatures. We are today doing the work that previous generations could only dream of doing, and the work is hard. That is the honest part of the K2-18b story. It is one thing to say that we now have the tools to study exoplanet atmospheres. It is another thing to actually extract a confident scientific conclusion from the data those tools produce. The technical challenges of transit transmission spectroscopy at the precision required for biosignature work are enormous. The systematic errors are subtle. The number of possible interpretations of any given spectrum is large. The methodology for distinguishing real signals from instrumental artifacts is still being developed. Every step of the analysis involves choices that made differently can produce different answers. The K2-18b debate is in a sense the field discovering for itself how hard the work is going to be. This is not a discouraging realization. It is just the realization that anyone who has worked in any difficult science is familiar with. The first attempts at any new kind of measurement are always messy. The methods get refined over time. The systematic errors get mapped out. The community develops standards for what counts as a robust detection. None of this happens overnight. None of this happens without controversy. The K2-18b debate is what it looks like when a field is in the early phases of working out its standards in real time with public attention, pressuring the process and high-stakes claims raising the temperature of the discussion. What we can take from this as people who are listening from outside the technical community is something more reflective. We are alive at the historical moment when this work is being done. We get to watch it unfold, whatever the answer turns out to be on K2-18. The broader project of looking for life beyond Earth has now begun in earnest with real data and real arguments and real progress. We are in some quiet way witnesses to the start of a long process that will continue across decades, possibly across centuries, possibly until our species answers the question or stops being able to ask it. I find this a strangely calming thought. The question of whether we are alone in the universe is one of the oldest and largest questions human beings have ever asked. For most of history, the question had no chance of being answered in any specific lifetime. Today, we cannot be sure that the question will be answered in our specific lifetimes either, but we can at least be sure that the answering process has begun. People are working on it. Telescopes are observing the few relevant targets, and spectra are being analyzed. Papers are being written and challenged and revised. The work is real. The work is happening. And whatever the work eventually reveals, our generation gets to be part of the moment when the question stopped being purely abstract and started being a problem people could actually attempt to solve. K2-18b in this larger frame is not so much an answer as a beginning. It is the first planet, or one of the very first, where humanity has had to seriously sit with ambiguous data from another world that might or might not be inhabited. It is the first time the standards of biosignature evidence have been applied to a real spectrum in public, with the world watching. It is the first time the careful methodological arguments that Carl Sagan's generation developed in theory have been put through their paces against actual JWST data. The case will be revised over the coming years as more data accumulates. The next paper, the next reanalysis, the next observation will all add to the picture. The picture itself will become clearer eventually over a longer timescale than any of us can wait through impatiently. Tonight, what we can do is hold the picture as it currently stands. A small reddish star 124 light-years away in the constellation Leo. A planet about 2.5 times the size of Earth in the habitable zone, transiting its star every 33 days. An atmosphere that probably contains methane and probably contains carbon dioxide, with a contested signal that might or might not include dimethyl sulfide. A research community that has not converged on what any of it means. A telescope currently in orbit at the second Lagrange point, scheduled for further observations of the same target. A planet that, whatever it harbors, has become the most carefully studied, potentially habitable world humanity has ever examined. This is where we are, not at the end of the story, at an early chapter with much of the narrative still to be written. The argument continues, the data accumulates, and the instruments keep running. And K2-18b, indifferent to all of it, continues its quiet 33-day orbits, sending its light across 124 years of empty space toward our small planet, where careful people are still trying to figure out what the light is actually telling us. Think back gently to where you were 124 years ago. That is, of course, a strange thing to ask, because you were almost certainly not yet here. Whoever your great-grandparents were, perhaps your great-great-grandparents, they were the people alive at that point. The world they were living in was a different world. The first commercial radio broadcasts had not yet happened. Powered flight was a few years old, fragile and experimental. Most of the world's energy still came from coal and from animals. The light bulb was a recent invention. The discoveries of quantum mechanics and general relativity were still ahead in the hands of physicists who were, at the moment we are talking about, still graduate students or younger. That is when the light left K2-18b that JWST was looking at when its 2025 paper was being written. The photons that arrived at the telescope that passed through the planet's atmosphere on their way out of its system that traveled for 124 years through the dark between stars that landed on JWST's mirror and were focused into its instruments and analyzed by its detectors, those photons started their journey when none of us was alive. The world they left was the world of our great-grandparents. The world they arrived in is the world of us sitting here listening to a voice describe their journey. There is something quietly intimate about this kind of transit, light-time-wise. The star and the planet were doing their orbits. The atmosphere was holding whatever it holds, and a particular set of photons happened to be released in just the right direction to eventually intersect with our planet a century and a quarter later. None of the people on Earth at the time those photons left could have known that the photons would eventually be analyzed by an instrument whose name they would not have understood, looking for signatures of substances that, with one or two exceptions, had not yet been catalogued by chemistry. The transit was happening. We just were not equipped to receive it. Now we are, more or less. I want to sit with what it means for you specifically to be alive at the moment when these photons are arriving. Because there is, I think, a privilege in the timing that is worth noticing. Your specific life intersects with the K2-18b photon stream in a particular way. The light that JWST analyzed in its 2023 observations left the planet around 120 years ago. The light that JWST analyzed in its 2025 MIRI observations left around 123 years ago. The light that future JWST observations will analyze will have left more recently, but always with that same 124-year lag. Throughout your life, the planet has been continuously sending light toward our part of the galaxy. While you were a child, K2-18b was orbiting its red dwarf. While you went to school, while you started whatever job you ended up in, while you fell in or out of love, or made the various decisions that constitute your specific biography, The planet was orbiting, and the light it sent toward us during all those years has been steadily approaching day after day, year after year. Some of that light is still in transit between K2-18b and Earth, and will be arriving for the rest of your life and well beyond. Whatever future observations are made, they will be analyzing photons that left during the years when you were alive, but were old enough to potentially be aware that this kind of work was being done. That overlap between your life and the photon stream is small in absolute terms. Most of the light that has been arriving from K2-18b has been doing so since long before any human was paying attention. But the small overlap that does intersect with your specific life is the part that contains the JWST observations and the unfolding scientific argument. You happen to be alive at the moment when humans are first trying to interpret the signals from this specific planet, and the signals that are being interpreted left the planet during your lifetime. The two timelines, your life and the K2-18b biosignature debate, are genuinely entangled, and the entanglement runs in the other direction too. The discussion, you have been listening to the slow walk through Madhusudhan's Hycean hypothesis, and the methane and carbon dioxide, and the contested dimethyl sulfide, and the Luque reanalysis, and the Shortall alternative is happening in your lifetime, in part because of the broader scientific developments that have happened over your lifetime as well. The James Webb Space Telescope was being designed and built throughout the early decades of your adulthood, depending on when you were born. The Kepler mission was producing its catalogue of exoplanet discoveries during a stretch of your life. The first exoplanet 51 Pegasi b was discovered when you, depending on age, were in school in your early career or already settled into adulthood. Your lifetime more or less is the lifetime over which exoplanet science went from speculation to data, and from data to detailed atmospheric analysis. You did not just happen to be alive while it was happening. You happened to be alive during exactly the stretch when it became possible. I do not say any of this to flatter your generation or to make you feel important. I say it to point out gently that the timing of any given person's life is in some real sense a kind of windfall. Most generations of human beings have not been alive during periods when major shifts in our cosmic self-understanding were unfolding. Most lives have happened during stretches of the long human history when the universe was scientifically much smaller than it is now. Your life is happening during a stretch when the universe is becoming detectably larger and stranger by the year, and when the questions about whether other planets are inhabited are stopping being abstract and starting to be empirical. That is not a small piece of timing. It is, by historical standards, an unusual moment to have been alive for. You can let that sink in if it helps. There is no particular action required. The shift is happening regardless of whether you do anything about it. You are not personally responsible for advancing the science. You are simply a person who happens to be alive while other people, the careful astronomers and atmospheric chemists and statistical analysts who have been doing this work, are working through the K2-18b problem in real time. Your role for tonight, at least, is to know that the work is happening and to let yourself rest and to fall asleep with the knowledge that 124 light years away, a small reddish star is hosting a planet whose atmosphere is being studied, and that the studying will continue regardless of whether you are awake or asleep. The planet itself is not waiting for you. The planet is doing what it has been doing for billions of years, which is orbiting its star, weathering its own kind of weather, holding whatever atmosphere it holds, possibly hosting biology, and possibly not. None of the work the planet is doing depends on your attention. None of the photons it is sending are for you specifically. But you are alive at the moment when at least some of those photons are being analyzed by the most capable telescope our species has ever built, and the analysis is unfolding in your specific present in the same century in which you happen to exist. There is a softness I want to bring into this part of the drift, because we are getting close to the end of the night, and the technical detail is largely behind us. What remains is something quieter. The question of whether there is life on K2-18b is for tonight undecided. You can fall asleep without an answer. The lack of an answer is not a problem. The lack of an answer is in fact the most interesting thing about the current moment in this story. We do not know. We are in the process of trying to find out. The trying is a real thing happening in real laboratories with real instruments in real time while you rest. I find it worth pausing for a moment on the long view of cosmic time, because the K2-18b story sits inside it in a particular way. The universe is roughly 13.75 billion years old. Earth is roughly 4.5 billion years old. Life on Earth is roughly 4 billion years old, give or take. Our species has existed for perhaps 300,000 years. Civilization in any recognizable form has existed for perhaps 10,000. The scientific revolution that eventually produced telescopes capable of looking at exoplanet atmospheres has existed for perhaps 400 years. The technology specifically capable of doing what JWST does has existed for less than 5 years. We are very new on cosmic timescales. The question of whether other worlds host life is by contrast very old. The question has been implicit in human curiosity since the first time someone looked at the night sky and wondered. The mismatch between how long the question has been askable and how long we have been able to ask it with real data is in a sense the longest gap in any major scientific question we have ever finally been able to start addressing. K2-18 sits at the front edge of that closing gap. It is not the answer. It might never be the answer. But it is one of the first concrete cases where the data and the question have come close enough together to actually intersect. Whatever happens with the K2-18b debate over the coming years, the fact that the debate is even possible is itself a piece of cosmic historical significance that does not depend on the eventual resolution. The closing of the gap, the moving of the question from speculation toward data, is the underlying event. K2-18b is the first specific test case. If the planet hosts biology, it has been hosting it for who knows how long and will continue hosting it regardless of when our science catches up to confirming the fact. If the planet does not host biology, it has been not hosting biology for the same long stretch, and the absence will be confirmed eventually by the same accumulating evidence. Either way, the truth of the matter is already settled somewhere in the universe, even though we do not yet know it. Our knowing or not knowing makes no difference to the planet. The work of finding out is in that sense entirely on our side. This is the kind of relationship with another world that I find when I sit with it to be quietly beautiful. We will never visit K2-18b. We will never sample its atmosphere directly. We will never see with our own eyes whatever it has under its clouds. The planet in any practical sense is permanently unreachable, and yet we are figuring it out slowly through careful spectroscopy and careful statistical analysis and careful argument among different research teams. We have built an apparatus JWST that lets us examine the air of a world we cannot visit. We are using that apparatus with all its limitations to ask one of the most ancient questions our species has asked. The answer is for now ambiguous. The asking is real. I would like you to feel as we move toward the close of this drift that you are part of a long lineage of human beings who have looked up at the sky and wondered about other worlds. Most of those people had no chance of getting any answer at all. They had to settle for speculation, for storytelling, for whatever satisfaction comes from the asking itself. You are part of the first lineage that has any chance of getting a real answer. The answer might come in your lifetime. It might not. But the asking in your lifetime is now connected to specific data being analyzed by specific scientists who are using specific instruments to look at specific candidate planets. And that connection is itself a meaningful change from where the human species has been for most of its history. You can let yourself rest in that connection in whatever way makes sense for you tonight. Whether you fall asleep with the K2-18b debate still in your mind, or whether you fall asleep on some other thought entirely, the science will continue without you. JWST will continue observing. Madhusudhan and his team will continue their analyses. Luque and Wellbanks and Shortall and Seeger and Taylor and the other careful scientists involved will continue their work. The picture will slowly become clearer. Not necessarily tomorrow and not necessarily this year, soon. But over time, with patience, with more data, with more methodology refinement, the case will move toward whatever answer the data eventually supports. Tonight, your part of the work is to rest. The science needs people who can support it through long careers with steady attention and careful judgment. That is not your job tonight. Tonight your job is to listen to a voice describe one of the more genuinely interesting open questions in modern astronomy, and to let yourself drift towards sleep with the knowledge that other people are taking care of the question, and that the question itself is being taken seriously, and that the universe will continue answering it in its own slow way without requiring anything from you. The planet is still there, the light is still arriving, and the argument continues. And you here in your specific room on this specific evening are part of the small slice of human history in which any of this is even possible to wonder about with real data. That is in its quiet way enough. We have come a long way tonight slowly through one of the more genuinely unresolved chapters in modern astronomy. Let me name what we have walked through briefly before the voice fades out. We started with a planet K2-18b, 124 light-years from Earth in the constellation Leo, orbiting a small reddish star called K2-18 once every 33 days. We met the people who first established that planet. Like this exist at all the Swiss astronomers, Michel Mayor and Didier Queloz, whose 1995 discovery of 51 Pegasi b around an ordinary sun-like star opened the entire field of exoplanet science, and who shared the Nobel Prize in 2019 for that discovery. We walked through the development of the James Webb Space Telescope, launched in December of 2021 and operational from mid-2022, with its 3 relevant instruments named NIRS and MIRI, and we walked through the technique of transit transmission spectroscopy that allows JWST to study the atmospheres of distant worlds. We met Nikku Madhusudhan and his team at the University of Cambridge, who in 2021 proposed the Hycean hypothesis, a new category of potentially habitable planet defined by a global liquid water ocean beneath a hydrogen-rich atmosphere. We walked through their 2023 JWST observations that detected methane and carbon dioxide in K2-18b's atmosphere with a tentative hint of dimethyl sulfide. We walked through their April 2025 follow-up paper in the astrophysical journal Letters, which reported a 3 sigma detection of dimethyl sulfide and dimethyl disulfide, both potential biosignature gases. We walked through the response from the broader scientific community. Sarah Seeger at MIT, calling for the standards of biosignature evidence to be applied. Jake Taylor at Oxford, questioning the statistical methodology. Louise Wellbanks at Arizona State University and Matthew Nixon at the University of Maryland, publishing a reanalysis showing that the apparent features depended on choices in wavelength binning. Raphael Luque and his colleagues at the University of Chicago publishing the most thorough reanalysis in astronomy and astrophysics in August of 2025, concluding that the evidence for the contested biosignature gases was insufficient when the full JWST dataset was analysed jointly. Oliver Shortall and Nicholas Wogan separately challenging the Hycean interpretation itself on geochemistry grounds. The Cambridge team responding to all of these challenges and standing by their own interpretation. The argument unfolding in real time in public with no clean resolution yet in sight. We placed all of this in the longer historical frame going back to Carl Sagan's 1993 Nature paper, which used the Galileo spacecraft to do a thought experiment in detecting life on Earth from space. That paper laid the groundwork for biosignature theory. The K2-18b debate is the first time the framework Sagan and his colleagues developed has been seriously applied to a real exoplanet spectrum with no ground truth available. We are, in some real sense, doing now what previous generations could only dream of doing, and we placed K2-18b in its broader context within the JWST exoplanet program. The TRAPPIST-1 system 40 light-years away, with its 7 Earth-sized planets, and its 3 habitable zone candidates, TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f. LHS 1140b, 49 light-years away, possibly a water world with its own atmospheric mysteries. The broader catalogue of nearly 6,000 confirmed exoplanets with dozens of potentially habitable candidates among them. The competing demands on JWST's observing schedule. The next generation of telescopes still many years from completion that will eventually take over this kind of work. What we did not do tonight was settle the question. We could not. Nobody can with the data currently available. The state of the field as of early 2026 is that K2-18b has methane and probably carbon dioxide in its atmosphere, that the additional sulfur-based signals are contested, that the Hycean interpretation is one of several possibilities that fit the bulk properties of the planet, and that future JWST observations will continue to refine the picture. The argument is genuine, the data is real, and the interpretation is open. If you want to hold one piece of all this as you fall asleep, let it be the broader fact about our specific moment in time. We are alive at the historical instant when the question of life beyond Earth has stopped being purely speculative and has become a real ambiguous, hard-to-interpret data analysis problem. The K2-18b debate is what that transition looks like in practice, with all its messiness and all its public arguments. Whatever the eventual answer turns out to be, the asking itself is now happening with real instruments, real data, and real careful thought. Our generation, whatever else we manage to accomplish, gets to be part of that. Before we let this drift end, I want to thank you for being here. Cosmic Drift is a small project made for evenings exactly like this one for people who want a quiet voice and a slow piece of cosmic science to carry them towards sleep. Every person who listens through the long stretch of the technical material, who lets the unfolding of a contested astronomical claim become part of their settling into rest, is what makes this channel possible. If you have enjoyed tonight's drift, the gentlest thing you can do is hit the like button and subscribe to the channel. It is a small gesture. It costs you nothing, but it tells the recommendation algorithms that this kind of slow, patient space documentary is worth recommending to other people who might need it. We are not asking for anything more than that. If you have already subscribed, thank you genuinely. That means more than you might realize. And now, as we close, I want to leave you with one last image. 124 light-years away in the constellation, Leo, a small reddish star, is hosting a planet a little larger than Earth, in the part of its orbit where liquid water could exist if the atmospheric conditions were right. The planet is right now doing its slow 33-day orbit, transiting in front of its star at regular intervals, as it has been doing for billions of years. Its atmosphere is what it is, with whatever combination of methane and carbon dioxide and other gases it actually has. Something is happening inside that atmosphere on that planet, possibly involving biology and possibly not. The light from those events is at this exact moment partway across the gulf between K2-18b and Earth, traveling at the speed of light, scheduled to arrive at our planet 124 years from when it left. If you are alive when those photons arrive, you may or may not still be paying attention to K2-18b. The argument may or may not have settled by then. The science of biosignature detection will almost certainly have moved on to other planets and other instruments and other debates. But tonight, in this specific window of cosmic time, you are part of the small early generation of humans who got to know that this question was being asked at all. That is enough for tonight. The question is in good hands. The instruments are working and the careful scientists are doing their work. You can rest. The next JWST observation of K2-18b is already on the schedule. The argument is slowly still unfolding. Madhusudhan's team will produce more analyses. The Reanalysis teams will continue their independent work. The case will eventually settle into whatever shape the evidence supports. Tonight the case is open, the voice is fading, and the drift is ending. Sleep well. The planet is still orbiting. The photons are still in transit, and the careful people who are working on the question will continue working on it tomorrow while you rest. Thank you for letting us carry you through the long, slow story of one of the more honest, unresolved chapters in modern astronomy. The light is on its way, the argument continues, and K2-18b, indifferent to all of it, keeps doing what it has always done in its quiet corner of the constellation Leo, sending its slow signal across the dark for whatever future generation of careful astronomers will eventually catch up to whatever truth the planet contains. Good night.